Imagine flipping a switch and suddenly you're moving at the speed of light, 300,000 kilometers per second. The entire Earth would become a blur beneath you. You could circle our planet 7.5 times in a single heartbeat. You would reach the Moon in just over 1 second, and Mars in 3 minutes. But here's what nobody tells you about traveling at light speed. The universe would transform into something completely alien. Today, we're exploring what would really happen if we could travel at light speed right now. If you're fascinated by the mind-bending possibilities of our universe, make sure to subscribe to this channel and hit the thumbs up. And here's a question for you. If you could travel at light speed for just 1 day, where in the universe would you go? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. Let's start with the brutal truth. According to Einstein's special relativity, it's physically impossible for anything with mass to reach the speed of light. Not difficult, not challenging, impossible. As you accelerate toward light speed, your mass effectively increases, requiring more and more energy to go faster. To actually reach light speed, you'd need infinite energy. All the energy in the observable universe wouldn't be enough, but let's imagine we found a loophole, some exotic physics that lets us achieve the impossible. What would happen? First, the universe around you would undergo a complete transformation. This isn't speculation, it's based on confirmed physics that we observe every day in particle accelerators and cosmic ray detections. As you approach light speed, something called relativistic aberration would compress your entire field of view into a tiny circle directly in front of you. Stars behind you would appear to swing around and crowd into your forward vision. The familiar constellations would be completely unrecognizable. But it gets weirder. The Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes, would shift all the light around you. Stars ahead would blue shift, their light compressed to higher frequencies. What started as gentle red starlight would shift through the spectrum, orange, yellow, white, blue, violet, then beyond human vision into ultraviolet, X-rays, and eventually deadly gamma rays. Meanwhile, stars behind you would redshift into invisibility, their light stretched into radio waves your eyes can't detect. At 90% of light speed, the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, would blue shift into visible light. You'd see the birth of the universe glowing all around you. Push closer to light speed, and this ancient light would become a lethal storm of gamma radiation. The empty vacuum of space would literally glow with deadly energy. The visual distortions would be just the beginning. Time dilation, proven by countless experiments from GPS satellites to particle accelerators, would fundamentally alter your experience of reality. At 99.9% of light speed, time would slow to a crawl. What feels like 1 year to you would be 22 years on Earth. Your watch would tick normally from your perspective. Your thoughts would flow at their usual pace, but the universe outside would be racing through time at an incredible rate. Push even closer to light speed, 99.999%, and the effect becomes extreme. 1 year of your time equals 223 years on Earth. At this speed, you could travel to the center of our galaxy in what feels like 20 years, but Earth would age 27,000 years in your absence. Your friends, your family, your entire civilization would be ancient history by the time you return. Imagine flipping a switch and suddenly you're moving at the speed of light, 186,000 miles per second. The entire Earth would become a blur beneath you. You could circle our planet 7.5 times in a single heartbeat, reach the Moon in just over 1 second, Mars in 3 minutes. But here's what nobody tells you about traveling at light speed. The universe would transform into something completely alien. Time itself would betray you, and the very atoms in your body would rebel against the journey. Today, we're exploring what would really happen if we could travel at light speed right now. And trust me, it's far stranger than science fiction has ever dared to imagine. If you're fascinated by the mind-bending possibilities of our universe, make sure to subscribe to this channel and hit that notification bell. I'm just starting my journey on YouTube, and your support means everything to me. Here's a question for you. If you could travel at light speed for just one day, where in the universe would you go and why? Drop your answer in the comments below. I'll feature the most creative response in my next video. Now let's begin. Let's start with the brutal truth. According to Einstein's special relativity, it's physically impossible for anything with mass to reach the speed of light. Not difficult, not challenging, impossible. As you accelerate toward light speed, your mass effectively increases, requiring more and more energy to go faster. To actually reach light speed, you'd need infinite energy. All the energy in the observable universe wouldn't be enough. But let's imagine we found a loophole, some exotic physics that lets us achieve the impossible. What would happen? First, the universe around you would undergo a complete transformation. This isn't speculation, it's based on confirmed physics that we observe every day in particle accelerators and cosmic ray detections. As you approach light speed, something called relativistic aberration would compress your entire field of view into a tiny circle directly in front of you. Stars behind you would appear to swing around and crowd into your forward vision. The familiar constellations would be completely unrecognizable. But it gets weirder. The Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes, would shift all the light around you. Stars ahead would blue shift, their light compressed to higher frequencies. What started as gentle red starlight would shift through the spectrum: orange, yellow, white, blue, violet, then beyond human vision into ultraviolet, X-rays, and eventually deadly gamma rays. Meanwhile, stars behind you would redshift into invisibility, their light stretched into radio waves your eyes can't detect. At 90% of light speed, the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, would blue shift into visible light. You'd see the birth of the universe glowing all around you. Push closer to light speed, and this ancient light would become a lethal storm of gamma radiation. The empty vacuum of space would literally glow with deadly energy. The visual distortions would be just the beginning. Time dilation, proven by countless experiments from GPS satellites to particle accelerators, would fundamentally alter your experience of reality. At 99.9% of light speed, time would slow to a crawl. What feels like 1 year to you would be 22 years on Earth. Your watch would tick normally from your perspective, your thoughts would flow at their usual pace, but the universe outside would be racing through time at an incredible rate. Push even closer to light speed, 99.999%, and the effect becomes extreme. 1 year of your time equals 223 years on Earth. At this speed, you could travel to the center of our galaxy in what feels like 20 years, but Earth would age 27,000 years in your absence. Your friends, your family, your entire civilization would be ancient history by the time you returned. This isn't science fiction, it's observed fact. Particles called muons, created when cosmic rays hit our atmosphere, demonstrate this perfectly. Muons decay in just 2.2 microseconds, barely enough time to travel 660 meters at near light speed, yet we detect them at Earth's surface, having traveled through 10 kilometers of atmosphere. How? Time dilation. From the muon's perspective, it only travels a few hundred meters before decaying. From our perspective, its internal clock runs so slowly that it survives the full journey. the Large Hadron Collider accelerates protons to 99.99999% of light speed. At this velocity, the protons experience such extreme time dilation that 1 second for them equals hours in the outside world. We've literally created time travelers, albeit microscopic ones, thousands of times per second in our particle accelerators. But traveling at true light speed would introduce paradoxes that break our understanding of physics. At exactly light speed, time dilation becomes infinite. Time would stop completely. From your perspective, you would arrive at your destination the instant you departed, no matter how far away it was. You could travel to the edge of the observable universe, 46 billion light-years away, in zero time. But here's the paradox. If no time passes for you, how can you experience the journey? How can you think, observe, or even exist in any meaningful way? This connects to a deeper truth about light itself. Photons, particles of light, don't experience time. From a photon's perspective, it's absorbed the instant it's emitted, whether it travels across a room or across the universe. The cosmic microwave background photons reaching Earth right now were emitted 380,000 years after the Big Bang and have traveled for 13.8 billion years, but from their perspective, no time has passed at all. Length contraction adds another layer of impossibility. As you approach light speed, distances in your direction of travel compress. At 90% light speed, distances shrink to 44% of their original length. At 99.9%, they shrink to just 4.5%. The 46 billion light-year journey to the edge of the observable universe would measure just 2 billion light-years from your perspective. At true light speed, length contraction becomes infinite. The entire universe would compress to zero thickness in your direction of travel. Every destination would be zero distance away. You wouldn't travel through space. Space itself would cease to exist in any meaningful way. You'd exist in a two-dimensional universe with no depth, no forward or backward, just an infinitely thin slice of reality. The energy requirements alone make light-speed travel impossible with any conceivable technology. Accelerating just 1 kilogram to 90% light speed requires energy equivalent to burning 21 million tons of coal. To reach 99%, you'd need 200 million tons. For 99.9%, 2 billion tons. The energy curve rises exponentially, approaching infinity as you near light speed. The space shuttle, fully fueled, could theoretically accelerate its payload to just 0.00005% of light speed if it converted all its fuel to kinetic energy with perfect efficiency. To reach even 1% of light speed would require a fuel tank larger than Earth. These aren't engineering challenges, they're fundamental limits imposed by the universe itself. This isn't science fiction, it's observed fact. Particles called muons, created when cosmic rays hit our atmosphere, demonstrate this perfectly. Muons decay in just 2.2 microseconds, barely enough time to travel 660 meters at near light speed. Yet we detect them at Earth's surface, having traveled through 10 kilometers of atmosphere. How? Time dilation. From the muon's perspective, it only travels a few hundred meters before decaying. From our perspective, its internal clock runs so slowly that it survives the full journey. The Large Hadron Collider accelerates protons to 99.99999% of light speed. At this velocity, the protons experience such extreme time dilation that 1 second for them equals hours in the outside world. We've literally created time travelers, albeit microscopic ones, thousands of times per second in our particle accelerators. But traveling at true light speed would introduce paradoxes that break our understanding of physics. At exactly light speed, time dilation becomes infinite. time would stop completely. From your perspective, you would arrive at your destination the instant you departed, no matter how far away it was. You could travel to the edge of the observable universe, 46 billion light-years away, in 0 time. But here's the paradox: if no time passes for you, how can you experience the journey? How can you think, observe, or even exist in any meaningful way? This connects to a deeper truth about light itself. Photons, particles of light, don't experience time. From a photon's perspective, it's absorbed the instant it's emitted, whether it travels across a room or across the universe. The cosmic microwave background photons reaching Earth right now were emitted 380,000 years after the Big Bang and have traveled for 13.8 billion years, but from their perspective, no time has passed at all. Length contraction adds another layer of impossibility. As you approach light speed, distances in your direction of travel compress. At 90% light speed, distances shrink to 44% of their original length. At 99.9%, they shrink to just 4.5%. The 46 billion light-year journey to the edge of the observable universe would measure just 2 billion light-years from your perspective. At true light speed, length contraction becomes infinite. The entire universe would compress to 0 thickness in your direction of travel. Every destination would be 0 distance away. You wouldn't travel through space. Space itself would cease to exist in any meaningful way. You'd exist in a two-dimensional universe with no depth, no forward or backward, just an infinitely thin slice of reality. The energy requirements alone make light-speed travel impossible with any conceivable technology. Accelerating just 1 kilogram to 90% light speed requires energy equivalent to burning 21 million tons of coal. To reach 99%, you'd need 200 million tons. For 99.9%, 2 billion tons. The energy curve rises exponentially, approaching infinity as you near light speed. The space shuttle, fully fueled, could theoretically accelerate its payload to just 0.00005% of light speed if it converted all its fuel to kinetic energy with perfect efficiency. To reach even 1% of light speed would require a fuel tank larger than Earth. These aren't engineering challenges, they're fundamental limits imposed by the universe itself. But the energy problem pales compared to what happens when you hit interstellar dust. Space isn't empty, it contains about 1 hydrogen atom per cubic centimeter, plus dust grains, cosmic rays, and magnetic fields. At everyday speeds, these particles are harmless. At light speed, they become apocalyptic. A single hydrogen atom hitting you at light speed would release energy equivalent to a 14-kiloton nuclear bomb, nearly as powerful as the weapon that destroyed Hiroshima. A dust grain would hit with the force of multiple hydrogen bombs. Speaking of the impossibilities of light-speed travel, if you want to dive deeper into the fundamental physics that makes this impossible, check out my video. This is why we can't travel at light speed, where we explore how time dilation, mass increase, and the fabric of space-time itself conspire to keep us forever below the speed of light. The link is in the description below and on the card above. Now back to our thought experiment. Even at 90% light speed, the situation is catastrophic. Hydrogen atoms would slam into your spacecraft with the energy of high-speed bullets. The kinetic energy of each impact would be about 10,000 times greater than the particle's rest mass. Your spacecraft would need shielding so thick that accelerating it becomes even more impossible. Some physicists have calculated that traveling to the nearest star at near light speed would be like flying through a particle beam weapon for years. The radiation would be lethal long before impact became an issue. As you accelerate, the cosmic microwave background radiation blue shifts into a deadly gamma-ray laser pointed directly at you. At 99.9% light speed, this gentle echo of the Big Bang becomes radiation millions of times more intense than standing next to a nuclear reactor core. The empty vacuum of space literally becomes radioactive. From your perspective, your own body would betray you in ways that seem pulled from horror fiction. The electromagnetic forces holding your atoms together propagate at light speed. As you approach this cosmic speed limit, these forces can't keep up. The front of each atom would try to race ahead while the back lags behind. Molecular bonds would stretch and distort. At speeds extremely close to light speed, the very concept of solid matter breaks down. You wouldn't just die, you'd dissolve into a cloud of subatomic particles. But let's push our imagination further. Suppose we had some magical technology that protected us from all these effects. What would navigation look like? The relativistic Doppler effect would make star recognition impossible. Every navigation beacon, every familiar constellation would be compressed into that tiny forward circle, blue shifted beyond recognition. You'd be flying blind through a universe that looks nothing like our star charts. The Breakthrough Starshot project, announced in 2016, aims to send tiny light sails to Proxima Centauri at 20% light speed. Even at this modest velocity, the engineering challenges are staggering. The spacecraft would need to survive acceleration of 10,000 Gs, endure years of cosmic ray bombardment, and somehow transmit data back to Earth across 4 light-years. And this is for a probe weighing just grams, not a crude vessel. Time dilation would create profound communication problems. Messages from Earth would be red-shifted and time compressed from your perspective. A year-long transmission from mission control would arrive, compressed into days or hours, depending on your speed. Your replies would be blue-shifted and time-stretched. A simple systems normal message could take years to fully transmit from Earth's perspective. Meaningful conversation becomes impossible when every exchange takes decades. The psychological effects would be devastating. Imagine watching Earth through a telescope as you travel. At near light speed, you'd see history unfold at terrifying speed. Continents would drift visibly. Ice ages would come and go in what feels like months. If you could somehow see human civilization, you'd watch empires rise and fall in fast forward, your entire species potentially evolving or going extinct during what feels like a brief journey to you. This temporal isolation would be absolute. Everyone you've ever known would age and die in what feels like days or weeks to you. Your civilization, your culture, even your language would be ancient history by the time you reached your destination. You wouldn't be a traveler, you'd be a temporal exile, forever cut off from your own era by the physics of space-time itself. The universe itself would age visibly around you. Stars would evolve through their life cycles in fast forward. Red giants would collapse into white dwarfs. New stars would birth from nebulae and die in supernovae, all compressed into a human timescale. You'd witness billions of years of cosmic evolution, watching the universe age and change in ways that would take normal observers eons to see. But perhaps the strangest effect would be on causality itself. At speeds very close to light speed, the order of events becomes ambiguous. Thanks to relativity of simultaneity, events that appear simultaneous to you might occur years apart for stationary observers, and vice versa. You could receive messages about events before they happen from your perspective, creating paradoxes that physics struggles to resolve. The Terrell-Penrose effect would distort space in mind-bending ways. Objects wouldn't just appear compressed, they'd appear rotated. A cube flying past at near light speed would appear twisted, showing faces that should be hidden. Spheres would look like ellipsoids. The entire three-dimensional structure of space would warp and twist in ways our brains never evolved to process. quantum effects add another layer of weirdness. The Unruh effect predicts that accelerating observers see empty space filled with warm radiation. At the extreme accelerations needed to reach light speed quickly, you'd see empty space glowing with thermal radiation. The vacuum itself would appear hot, filled with particles that don't exist for stationary observers. You'd literally be seeing particles that aren't there for anyone else. Your mass would increase from the perspective of outside observers, though you'd feel normal. At 90% light speed, your mass would appear to be about 2.3 times your rest mass. At 99.9%, you'd appear to have 22 times your normal mass. This isn't just mathematical abstraction. Particle accelerators must account for this mass increase when bending particle beams with magnetic fields. The energy stored in your motion would be tremendous. At near light speed, your kinetic energy would dwarf your rest mass energy. If you somehow stopped suddenly, that energy would be released in an explosion that would make nuclear weapons look like firecrackers. A 100-kilogram person traveling at 99.9% light speed carries kinetic energy equivalent to 10 billion tons of TNT, enough to devastate a small country. Let's talk about what happens to your spacecraft's propulsion at these speeds. As you approach light speed, your exhaust, whether it's hot gas, ions, or even photons, becomes less effective. This is due to the relativistic velocity addition formula. If you're traveling at 90% light speed and fire exhaust backward at 90% light speed, relative to your ship, it doesn't leave you at 180% light speed. Instead, it moves at just 99.4% light speed relative to stationary observers. The faster you go, the less thrust you get from the same exhaust velocity. This creates a vicious cycle. You need more energy to accelerate, but your propulsion becomes less efficient. It's like trying to run up an escalator that speeds up the faster you climb. The universe literally resists your attempts to reach light speed, implementing a cosmic speed limit through the very laws of physics. The Alcubierre drive, proposed in 1994, offers a potential loophole, not moving through space at light speed, but warping space itself. By contracting space in front of you and expanding it behind, you could theoretically reach distant stars without locally exceeding light speed. But the energy requirements are absurd. You'd need exotic matter with negative energy density equivalent to the mass of Jupiter. And recent calculations suggest the drive would create causality paradoxes, potentially allowing time travel into the past. Even if we could somehow achieve light speed, stopping presents its own impossibilities. At true light speed, you have infinite kinetic energy. Slowing down would require removing infinite energy. Where does it go? How do you brake when the universe has compressed to zero thickness in front of you? The physics breaks down completely, leaving us with paradoxes that have no resolution within our current understanding. The twin paradox becomes extreme at light speed. If you traveled to Alpha Centauri at light speed, zero time would pass for you while 4.3 years passed on Earth. But from your perspective, Earth would be traveling away from you at light speed, so shouldn't zero time pass there? The resolution involves acceleration. You must accelerate to reach light speed, breaking the symmetry. But at true light speed, the paradox becomes unresolvable because infinite time dilation creates mathematical singularities. Consider what happens to fundamental forces at extreme velocities. The electromagnetic force that holds atoms together propagates at light speed. As you approach this limit, the force carriers, photons, can barely keep up with your motion. Atoms would elongate in your direction of travel, electrons struggling to orbit nuclei that are racing away from them. Chemistry as we know it would cease to function. Your DNA would unravel, proteins would denature, and the molecular machinery of life would grind to a halt. The strong nuclear force mediated by gluons faces similar problems. While gluons themselves are massless and travel at light speed, the composite particles they bind, protons and neutrons, would experience extreme stresses. Nuclear physics simulations suggest that atomic nuclei would become unstable at velocities extremely close to light speed, potentially triggering spontaneous fission throughout your body. Let's examine what current technology tells us about near-light speed travel. The Parker Solar Probe, humanity's fastest spacecraft, reaches speeds of 430,000 miles per hour, just 0.06% of light speed. Even this modest velocity requires a complex trajectory using Venus's gravity for multiple assists. To reach just 1% of light speed would require propulsion systems thousands of times more powerful than anything we've built. Ion drives, our most efficient propulsion technology, achieve exhaust velocities of about 90,000 miles per hour. Even with perfect efficiency and a spacecraft that's 99% fuel, you'd reach only about 0.4% of light speed. Nuclear pulse propulsion studied in Project Orion might achieve 3 to 5%. Theoretical fusion rockets might reach 10 to 15%, but each step toward light speed requires exponentially more advanced technology. The interstellar medium becomes a deadly obstacle course at high speeds. Magnetic fields, usually measured in microgas, would compress and intensify from your perspective. At 90% light speed, a typical interstellar magnetic field would appear 10 times stronger and oscillate at 10 times the frequency. These fields would induce electrical currents in your spacecraft, heating it and potentially disrupting electronics. Cosmic rays pose an even greater threat. These high-energy particles, accelerated by supernovae and active galactic nuclei, already travel at significant fractions of light speed. When you're also moving at near light speed, head-on collisions would have energies approaching the Planck scale, where our understanding of physics breaks down. Each cosmic ray impact would be like a microscopic black hole forming and instantly evaporating in your spacecraft's hull. The bow shock formed by your passage through interstellar gas would create its own problems. Like a supersonic aircraft creating a sonic boom, a near-light-speed spacecraft would create a photonic boom, a shock wave of compressed electromagnetic radiation. This shock would heat interstellar gas to millions of degrees, creating a plasma shield around your vessel that would glow like a small star. Navigation becomes nearly impossible as you approach light speed. The cosmic microwave background, usually uniform in all directions, would appear as a brilliant searchlight dead ahead and fade to nothing behind you. This actually provides a universal reference frame. You could measure your absolute velocity through space by observing how blue-shifted the CMB appears, but it also means you're flying into an ever-intensifying radiation field. Gravitational effects add another layer of complexity. At extreme speeds, gravitational fields appear to change. A planet you're approaching wouldn't just pull you toward it. From your perspective, its gravity would have a component pushing you sideways, deflecting your trajectory in ways Newton never imagined. This gravitomagnetic effect, predicted by general relativity, has been measured by satellites like Gravity Probe B, but becomes extreme at relativistic speeds. The Shapiro delay would affect your journey in strange ways. Light passing near massive objects takes longer to travel than expected, as space-time curvature lengthens its path. At near light speed, you'd experience this effect dramatically. Flying past a star, you'd see its light delayed and distorted, creating multiple images and Einstein rings that would confuse any navigation system. Quantum entanglement, often misunderstood as allowing faster-than-light communication, provides no escape from light speed limits. While entangled particles correlate instantly regardless of distance, no information can be transmitted through entanglement alone. The universe seems carefully designed to prevent any form of faster-than-light information transfer, maintaining causality at all costs. The holographic principle suggests that information in a volume of space is limited by the area of its boundary, not its volume. At near light speed, the observable universe contracts in your direction of travel. Does this mean you have access to less information? Some physicists speculate that approaching light speed might fundamentally limit how much you can know about your destination before arriving. The biological impossibilities of light speed travel extend beyond radiation and molecular disruption. Your circadian rhythms, evolved over millions of years to match Earth's rotation, would have no reference point. The blue shifted starlight ahead would be millions of times brighter than the sun, while the universe behind you would be darker than the deepest cave. Your pineal gland, which regulates sleep through melatonin production in response to light, would be completely confused. Sleep might become impossible, or you might fall into a permanent dormant state. Even more fundamentally, the electrical signals in your nervous system propagate at speeds far below light speed, typically around 200 miles per hour for pain signals, up to 250 miles per hour for touch sensations. At near light speed, the relativistic effects on electromagnetic fields might interfere with neural transmission. Your thoughts could literally slow down or become scrambled as the physics of your own neurons struggles with the extreme environment. The cardiovascular system faces unique challenges. Blood pressure depends on the interplay between your heart's pumping and the elasticity of blood vessels. At extreme velocities, the relativistic effects on molecular bonds could alter vessel elasticity in unpredictable ways. Your heart might pump normally from its perspective, while your blood vessels experience time differently, creating potentially fatal mismatches in pressure and flow. Let's consider what we could actually observe if we somehow achieved near-light speed travel. The COBE and WMAP satellites have mapped the cosmic microwave background in exquisite detail, showing tiny temperature fluctuations of just 1 part in 100,000. At 99% light speed, these gentle ripples would blue shift into a blinding gamma-ray beacon. The fossil radiation from the Big Bang would become a deadly weapon aimed directly at you. Stars would no longer look like stars. Instead of points of light, they'd appear as streaks or arcs due to the finite speed of light and your extreme velocity. The constellation Orion wouldn't just be distorted, it would be smeared across the sky in a psychedelic light show. The familiar patterns humans have used for navigation for millennia would be utterly unrecognizable. The interstellar medium contains complex molecules: water, ammonia, formaldehyde, even amino acids. At normal speeds, these drift harmlessly through space. At near light speed, each molecule becomes a high-energy projectile. A single water molecule hitting at 99% light speed carries the kinetic energy of a rifle bullet. A grain of cosmic dust would impact with the force of a bomb. Magnetic fields permeate the galaxy, typically at strengths of a few microgauss. The Voyager spacecraft have mapped these fields as they exit the solar system. At relativistic speeds, these weak fields would appear compressed and intensified. They'd induce electrical currents in any conductor, heating your spacecraft and potentially interfering with electronics. The galaxy's magnetic field would become a viscous medium resisting your passage. The Pioneer anomaly, a mysterious deceleration observed in distant spacecraft, took decades to explain. It turned out to be thermal radiation pressure from the spacecraft's own power source. At near light speed, similar subtle effects would be magnified enormously. The pressure from your own waste heat, normally negligible, could significantly affect your trajectory. Every photon emitted by your spacecraft would carry momentum, creating thrust you'd need to account for. Time dilation would affect not just aging, but fundamental processes like radioactive decay. Uranium-238, with a half-life of 4.5 billion years, would appear stable from your perspective while decaying rapidly in the outside universe. Medical isotopes used for imaging or treatment would behave unpredictably. The careful timing required for nuclear reactions would be thrown off, making nuclear power systems unreliable. The Casimir effect demonstrates that empty space seethes with quantum fluctuations, virtual particles popping into existence and annihilating. At extreme speeds, these fluctuations would blue shift into real, detectable particles from your perspective. The vacuum itself would appear to be boiling with activity, filled with electron-positron pairs and other particles that don't exist for stationary observers. GPS satellites must account for both special and general relativistic effects to maintain accuracy. Their clocks run faster due to reduced gravity but slower due to orbital velocity. The corrections are tiny, microseconds per day, but essential for navigation. At near light speed, these effects wouldn't be corrections but dominant factors. Time itself would become a fluid, mutable quantity that varies dramatically with tiny changes in velocity. The oh my god particle, detected in 1991, was a cosmic ray proton traveling at 99.999999999999999% of light speed. It carried the kinetic energy of a baseball thrown at 60 miles per hour, all in a single subatomic particle. If such particles exist naturally, imagine the energies involved in accelerating an entire spacecraft to even a fraction of that speed. Cherenkov radiation, the blue glow seen in nuclear reactors, occurs when particles exceed light speed in a medium like water. In the interstellar medium, with its trace gases and plasma, a near-light speed spacecraft might produce its own Cherenkov radiation, glowing with an eerie blue light. You'd be announcing your presence across light years, a beacon visible to any civilization with basic telescopes. The Woodward effect, a controversial proposal for reactionless thrust, claims that mass fluctuations during acceleration could produce net thrust without expelling reaction mass. Even if this effect exists, it would be subject to relativistic corrections at high speed. The very concepts of mass and acceleration become fluid near light speed, making any exotic propulsion system unpredictable. Gravitational waves, ripples in spacetime detected by LIGO, travel at exactly light speed. As you approach this cosmic speed limit, you'd be surfing alongside these waves. Binary black holes spiraling together would create a pattern of waves you'd experience differently than stationary observers. You might even generate detectable gravitational waves yourself, as any accelerating mass must according to general relativity. The cosmic web, the largest structure in the universe, consists of galaxy filaments separated by vast voids. At near light speed, this structure would appear compressed and distorted. Billion light-year filaments would scrunch into manageable distances from your perspective. You'd witness the large-scale structure of the universe in a way impossible for stationary observers, seeing patterns and connections hidden by the vastness of space. The fundamental problem with light-speed travel goes deeper than energy or engineering. It challenges the nature of existence itself. At exactly light speed, the Lorentz factor becomes infinite, creating mathematical singularities in every equation of physics. Mass becomes infinite, time stops, distances shrink to zero. These aren't just large numbers or extreme conditions, they're infinities that break mathematics itself. It's like dividing by zero. The universe simply says error and refuses to compute. Consider what happens to information at these speeds. The Landauer principle states that erasing information requires minimum energy and produces heat. At near light speed, with time dilation and length contraction, information processing would be warped beyond recognition. Your onboard computers would experience time differently than their own circuits. Data flowing through processors would be subject to relativistic effects, potentially corrupting calculations essential for navigation and life support. The vacuum of space isn't truly empty. It's filled with quantum fields that give rise to all particles and forces. The Higgs field, which gives particles their mass, would interact strangely with matter moving at extreme speeds. Some theoretical physicists speculate that approaching light speed might alter how particles couple to the Higgs field, potentially changing their effective mass in unpredictable ways. Tachyons, hypothetical particles that travel faster than light, illustrate why light speed is a fundamental barrier. If tachyons existed, they could never slow down to light speed, just as we can never speed up to it. Light speed isn't just a maximum, it's an impenetrable wall dividing the universe into two domains: the subluminal world we inhabit and a superluminal realm that may not exist at all. The Unruh effect predicts that accelerating observers see blackbody radiation, where inertial observers see none. The extreme accelerations needed to reach light speed quickly would bathe you in thermal radiation from empty space itself. The harder you accelerate, the hotter space appears. Push hard enough, and the vacuum would glow hotter than the surface of the sun, cooking you with radiation that doesn't exist for anyone else. String theory, if correct, adds extra dimensions to space-time, possibly 6 or 7 additional dimensions curled up at microscopic scales. At extreme speeds, these hidden dimensions might become relevant. The way particles and forces behave could change as relativistic effects probe scales where extra dimensions matter. You might experience physics that doesn't exist at normal speeds. The black hole information paradox highlights deep mysteries about information preservation in extreme conditions. As you approach light speed, you create an event horizon of sorts, a boundary beyond which information can't catch up to you. This might create information paradoxes similar to those plaguing black hole physics. What happens to information that can't reach you? Does it cease to exist from your perspective? Quantum decoherence, the process by which quantum systems lose their quantum properties through environmental interaction, would be dramatically affected by extreme speeds. The blue shifted radiation bombarding you would cause near instantaneous decoherence of any quantum systems. Quantum computers, should you have them aboard, would be impossible to maintain. Even the quantum processes in your own atoms would be disrupted. The anthropic principle, the observation that physical constants seem fine-tuned for life, extends to the speed of light itself. If light traveled much faster, stars would burn out too quickly for life to evolve. Much slower, and the universe would collapse before complex chemistry could develop. The speed of light isn't arbitrary, it's precisely what it needs to be for the universe to support observers like us. Dark energy, the mysterious force accelerating cosmic expansion, adds another wrinkle. As the universe expands, distant galaxies recede from us at increasing speeds. Galaxies beyond the cosmic event horizon are already receding faster than light, not through space, but because space itself is expanding. Even at light speed, you could never reach them. The universe has destinations that are fundamentally unreachable, regardless of your velocity. The many worlds interpretation of quantum mechanics suggests that every quantum event splits the universe into multiple branches. At near light speed, with countless particle interactions happening at relativistic energies, you might be creating branches at an unprecedented rate. Each collision with an interstellar atom, each blue shifted photon absorbed, could spawn new universes. You wouldn't just be traveling through space, you'd be fracturing reality itself. Closed time-like curves, paths through space-time that loop back to their own past, become possible in certain solutions to Einstein's equations involving near-light speed travel. The Gödel metric, the Alcubierre drive, and traversable wormholes all potentially allow time travel. But this creates grandfather paradoxes and causality violations that physics abhors. The universe seems to conspire to prevent these paradoxes, perhaps by making light-speed travel impossible. The simulation hypothesis, the idea that our universe might be a computer simulation, offers a unique perspective on light-speed limits. The speed of light might be the maximum rate at which the cosmic computer can process information. Trying to exceed it would be like trying to make a video game character move faster than the game engine can render. The universe might literally lag or crash if something moved too fast. Cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe, could theoretically allow faster-than-light travel by creating shortcuts through space. But recent observations have found no evidence for cosmic strings, and their existence would require physics beyond the standard model. Even if they exist, using them for travel would require technology indistinguishable from magic. The holographic principle suggests that all information in a volume of space is encoded on its boundary. As you approach light speed and space contracts in your direction of travel, you might be approaching the fundamental information limit of the universe. Perhaps light speed is unreachable because it represents the boundary between our three-dimensional reality and the two-dimensional hologram that encodes it. Observations of distant type Ia supernovae revealed that the universe's expansion is accelerating, earning the 2011 Nobel Prize in Physics. This means that even at light speed, most of the universe is already unreachable. Every second, more galaxies cross the cosmic event horizon, becoming forever inaccessible. The observable universe is shrinking, and no amount of speed can stop it. The Parker Solar Probe, humanity's fastest object, uses gravity assists from Venus to reach speeds of 430,000 miles per hour. But here's the sobering reality. Even if we could maintain that acceleration continuously for a human lifetime, we'd only reach about 0.5% of light speed. The probe experiences temperatures of 2,500 degrees Fahrenheit just from flying through the sun's corona at these slow speeds. At near light speed, the friction from interstellar hydrogen alone would generate temperatures hotter than the sun's core. Neutrinos, the ghost particles that barely interact with matter, offer a glimpse of what near light speed travel means. These particles zip through the Earth like it isn't there, with trillions passing through your body every second. The ice cube detector at the South Pole uses a cubic kilometer of ice to catch just a handful. At near light speed, regular matter would interact with the interstellar medium almost as weakly as neutrinos interact with us. You'd become ghost-like, existing in a different realm of physics. The twin paradox becomes even stranger when we consider biological rhythms. Your cells divide on regular schedules, your neurons fire in patterns, your heart beats in rhythm. At near light speed, these biological clocks would continue normally from your perspective, but race ahead compared to Earth. You might age 1 year while Earth ages 1,000, but that 1 year would feel completely normal to you. Every heartbeat, every breath, every thought would proceed at its usual pace while civilizations rise and fall in the outside universe. Quantum tunneling, where particles pass through barriers they shouldn't be able to cross, happens because of the wave nature of matter. At extreme speeds, the de Broglie wavelength of macroscopic objects becomes relevant. Your entire spacecraft might exhibit quantum behavior, potentially tunneling through barriers or existing in superposition states. The boundary between classical and quantum physics would blur in ways we can barely imagine. The Fermi paradox asks why we see no evidence of alien civilizations despite the vast number of potentially habitable planets. One possible answer: the speed of light truly is an absolute barrier. Every civilization, no matter how advanced, remains trapped in their stellar neighborhood. The universe might be teeming with life, but each species is isolated by the tyranny of distance and the cosmic speed limit. Metamaterials with negative refractive indices can make light appear to travel backward. Some physicists have speculated about space-time metamaterials that could alter the apparent speed of light in a region. But these exotic proposals require forms of matter that may not exist, and energy densities that dwarf anything we can produce. Even if possible, they wouldn't truly break the light-speed barrier, they'd just create the illusion of doing so. The Alcubierre white warp drive, a refined version of the original concept, reduces the energy requirements from Jupiter mass to asteroid mass by optimizing the warp bubble geometry. But it still requires exotic matter with negative energy density, something that has never been observed and may be physically impossible. Even if we could create it, recent calculations show the drive would generate causality paradoxes, potentially allowing travel into your own past. Time crystals, structures that repeat in time rather than space, were thought impossible until their creation in 2017. These bizarre states of matter challenge our understanding of thermodynamics and time itself. Some theorists wonder if space-time itself might have crystalline properties at the Planck scale, and whether exploiting these could offer new approaches to space travel. But even time crystals respect the speed of light. They're not shortcuts, but reminders of how strange physics becomes at extremes. The M drive, a proposed reactionless thrust device, claimed to produce thrust without expelling propellant, potentially enabling continuous acceleration to near light speed. After years of testing, no convincing evidence supports its function. The device likely produces false readings due to experimental error. This highlights a crucial point. Every proposed shortcut to light speed has either been debunked or requires physics we've never observed. Cosmic inflation, the exponential expansion of space in the universe's first fraction of a second, caused regions to separate faster than light. But this wasn't motion through space, it was space itself expanding. The distinction is crucial. Matter and energy are forever limited to subliminal speeds, but space-time itself faces no such restriction. This offers no help for space travel. We can't make space expand around us in controlled ways. The quantum Zeno effect shows that frequent observation can freeze a quantum system's evolution. At near light speed, the constant interaction with interstellar particles and radiation would constitute continuous observation. Your quantum state might become frozen, unable to evolve normally. This could affect everything from chemical reactions to consciousness itself, potentially making life impossible at extreme velocities. Bose-Einstein condensates, states of matter where atoms occupy the same quantum state, exhibit superfluidity and other exotic properties. Some physicists speculate that space-time itself might undergo phase transitions at extreme conditions, perhaps forming a sort of space-time condensate near light speed. If true, the properties of space itself would change as you accelerate, potentially creating an absolute barrier to further acceleration. The firewall paradox in black hole physics suggests that event horizons might be surrounded by high-energy particle curtains that incinerate anything passing through. Some theorists wonder if approaching light speed creates a similar firewall, a barrier of infinite energy that destroys anything trying to cross it. This would make light speed not just unreachable, but actively hostile to matter. Gravitational lensing shows how massive objects bend light paths. At near light speed, every star's gravity would lens the light around you in extreme ways. Multiple images of every star would appear, creating a hall of mirrors effect. Navigation would require accounting for not just where stars are, but where their gravitationally lensed images appear. The universe would become a cosmic kaleidoscope. The vacuum catastrophe, the 120 order of magnitude discrepancy between predicted and observed vacuum energy, remains physics' greatest unsolved problem. This mystery suggests we fundamentally misunderstand empty space. Perhaps the vacuum itself changes properties at extreme speeds, creating unexpected barriers to acceleration. The empty space you're traveling through might not be as empty or as simple as we think. Sonoluminescence, where collapsing bubbles in water produce light, demonstrates how extreme conditions can produce unexpected physics. The bubbles reach temperatures comparable to the sun's surface for brief instants. At near light speed, similar exotic phenomena might occur as you plow through the interstellar medium, creating unpredicted effects that make travel impossible or deadly. The Great Filter hypothesis suggests there's some nearly insurmountable challenge that prevents life from spreading throughout the galaxy. Perhaps the speed of light is that filter. Not a barrier to be overcome, but a fundamental wall that keeps every civilization confined to its home system. We search the stars for signs of intelligence, but maybe they're all trapped behind the same physics that traps us, forever isolated by Einstein's equations. Let's examine what happens to atoms themselves at extreme velocities. The electron clouds that define chemistry would distort dramatically. Bonds that are stable at rest might spontaneously break as electron orbitals elongate in the direction of travel. Water molecules might dissociate into hydrogen and oxygen. Complex proteins would unravel. DNA's double helix would stretch like a spring until it snaps. You wouldn't need to hit anything. Your own chemistry would rebel against the journey. The Breakthrough Starshot project, funded by Yuri Milner and endorsed by Stephen Hawking, aims to send tiny light sails to Proxima Centauri at 20% light speed. Even this modest goal requires a 100 gigawatt laser array, more power than most countries consume. The sail must be perfect to within atoms reflecting 99.999% of incoming light. A single defect would create a hot spot that vaporizes the entire sail, and this is for a probe weighing mere grams, not a human spacecraft. Plasma wake-field acceleration, used in next-generation particle accelerators, can achieve gradients of hundreds of gigavolts per meter. But even these extreme fields can only accelerate subatomic particles. Scaling up to accelerate macroscopic objects would require planet-sized accelerators consuming the energy output of entire civilizations. The Large Hadron Collider, 27 kilometers in circumference, accelerates protons to 99.99999% light speed. Imagine the size needed to accelerate a spaceship. The cosmic speed limit affects not just travel, but communication. SETI searches for alien signals, but any conversation with even the nearest star would take nearly 9 years per exchange. With stars hundreds or thousands of light years away, entire civilizations could rise and fall between messages. The speed of light doesn't just limit our bodies, it limits our minds, our culture, our ability to share knowledge across cosmic distances. Quantum entanglement, often misrepresented as enabling faster-than-light communication, actually preserves the speed limit. While entangled particles correlate instantly, no information travels between them. It's like having two coins that always land on opposite sides. Mysterious, yes, but useless for sending messages. Every attempt to use entanglement for communication fails, as if the universe actively prevents cheating its speed limit. The Podkletnov gravity shield, claimed to reduce gravitational effects, would theoretically enable easier acceleration to high speeds. But decades of attempts to replicate the effect have failed. Like cold fusion and perpetual motion machines, it joins the graveyard of physics claims that promise to revolutionize space travel. The pattern is clear. Every proposed shortcut either violates known physics or can't be reproduced. Frame dragging, where rotating massive objects twist space-time, has been confirmed by satellites like Gravity Probe B. Some theorists propose using rotating black holes or artificial rotating masses to create closed, time-like curves or reduce effective distances. But the rotation rates required would tear apart any known material, and the tidal forces near such objects would spaghettify anything approaching them. The Casimir effect demonstrates that parallel plates in vacuum experience attractive force due to quantum fluctuations. Some propose using this for exotic propulsion or to stabilize wormholes. But the effect is incredibly weak, producing less force than a butterfly's wing, even with perfectly conducting plates nanometers apart. Scaling up to useful levels would require materials and precision we can't achieve. Dark matter, comprising 85% of the universe's matter, interacts gravitationally but seems invisible to electromagnetic forces. If we could somehow convert our spacecraft to dark matter, would it slip through the interstellar medium unimpeded? Pure speculation, but it illustrates how desperately we search for loopholes in the cosmic speed limit. Every avenue we explore leads back to the same conclusion: light speed is absolute. The false vacuum hypothesis suggests our universe might exist in a metastable state, like a ball perched on a hill. If true, extreme energies, perhaps those involved in approaching light speed, could trigger vacuum decay, destroying not just the traveler, but potentially the entire universe in an expanding bubble of doom. This doomsday scenario is purely theoretical, but it shows how light speed might be a safety limit, protecting the universe from its own destruction. Closed time-like curves near rotating black holes theoretically allow time travel, but with catches that preserve causality. The Novikov self-consistency principle suggests that any time travel would be constrained to prevent paradoxes. You could observe the past, but not change it. Even in general relativity's most exotic solutions, the universe seems designed to prevent the paradoxes that faster-than-light travel would create. The measurement problem in quantum mechanics, how observation collapses wave functions, becomes acute at relativistic speeds. Different observers disagree on when collapse occurs, potentially leading to contradictory realities. This isn't just philosophical. It could mean that consciousness itself breaks down at speeds approaching light, making the journey not just physically, but mentally impossible. Negative mass, if it existed, would accelerate in the opposite direction of applied force. Pairing negative and positive mass could theoretically create self-accelerating systems that reach arbitrary speeds, but negative mass has never been observed and would violate multiple conservation laws. It's another beautiful theory destroyed by ugly facts. The information paradox extends beyond black holes to any extreme physics. As you approach light speed, information about your quantum state becomes increasingly scrambled from any outside observer's perspective. You might literally lose coherence as a physical system, dissolving into quantum noise. The universe might not allow macroscopic objects to maintain their identity at such speeds. Tachyon condensation in string theory suggests that faster-than-light particles, if they existed, would decay into subluminal particles. The universe seems to have a built-in mechanism for eliminating anything that violates the speed limit. Even in theoretical frameworks that allow superluminal motion, stability concerns bring everything back below light speed. The cosmic censorship hypothesis proposes that singularities, points where physics breaks down, are always hidden behind event horizons. Similarly, the universe might censor faster-than-light travel to prevent causality violations. Every loophole we find seems to come with its own prohibition, as if nature has thought of everything and closed every door. The speed of light isn't just a limit, it's a fundamental feature that keeps reality consistent. Consider the energy density of empty space at near-light speeds. The quantum vacuum, normally containing about 10 to the -9th joules per cubic meter, would appear to have energy density approaching that inside atomic nuclei from your perspective. Space itself would become thick, viscous, resistant to your passage. You'd be trying to push through a medium denser than any material known to science. The Penrose process theoretically allows extracting energy from rotating black holes by dropping matter into the ergosphere. Some have proposed using this to accelerate spacecraft to extreme speeds. But the logistics are impossible. You'd need to already be traveling at near-light speed to reach the black hole, defeating the purpose. and the tidal forces would destroy any spacecraft long before it could utilize the effect. Superluminal motion in astronomy, where objects appear to move faster than light, is actually an illusion caused by projection effects. Jets from quasars seem to travel at multiple times light speed, but it's a trick of geometry and light travel time. The universe teases us with apparent violations of the speed limit, only to reveal that they're mirages. Reality respects Einstein even when it seems not to. The chronology protection conjecture proposed by Stephen Hawking suggests the laws of physics prevent time travel on macroscopic scales. Quantum effects would destroy any would-be time machine before it could operate. If approaching light speed enables time travel, these same quantum effects might make the journey impossible. The universe seems to protect its timeline as jealously as it guards its speed limit. Metamaterial cloaking devices can make objects invisible by bending light around them. Some theorists propose space-time metamaterials that could bend space itself, creating shortcuts or reducing effective distances. But these would require exotic matter arrangements that may be fundamentally impossible, like trying to build a perpetual motion machine from real components that must obey thermodynamics. The quantum eraser experiment shows that quantum information can be retroactively determined, seeming to change the past. At near light speed, such quantum effects might scramble causality in ways that make coherent travel impossible. You might arrive at your destination before you left, or never arrive despite having departed. The journey might become a quantum superposition that never resolves into classical reality. Plasma shields have been proposed to protect spacecraft from interstellar medium impacts. A magnetic field would deflect charged particles, while a plasma shield absorbs neutral atoms. But at near light speed, the energy requirements become absurd. You'd need the power output of entire stars just to maintain the shield, defeating the purpose of travel. Every solution creates bigger problems. The Rindler horizon appears for constantly accelerating observers, similar to a black hole event horizon. As you accelerate toward light speed, this horizon would shrink, eventually cutting you off from most of the universe. You'd be trapped in an ever smaller bubble of causality, isolated from everywhere you're trying to reach. The destination would literally disappear behind an unreachable horizon. Cosmic rays with energies exceeding 10 to the 20th electron volts shouldn't exist. They should lose energy to the cosmic microwave background through the GZK cutoff. Yet we detect them, suggesting unknown physics at extreme energies. Perhaps approaching light speed triggers similar unknown effects that make travel impossible in ways we haven't discovered. The vacuum birefringence predicted by quantum electrodynamics causes empty space to act like a crystal, splitting light beams in strong magnetic fields. At near light speed, this effect might scatter your atoms like light through a prism, literally spreading you across space. Your coherent existence as a single object might become impossible. Sonoluminescence remains partially unexplained. We don't fully understand how collapsing bubbles produce such intense light. Similar exotic physics might occur in the bow shock of a near-light speed spacecraft. Unknown reactions between compressed space-time and quantum fields could create barriers we can't predict with current physics. The Schwinger limit marks where electric fields become strong enough to spontaneously create particle-antiparticle pairs from vacuum. At near light speed, electromagnetic fields from your interaction with interstellar medium might exceed this limit, creating a cascade of particle production that acts like friction, preventing further acceleration. Loop quantum gravity suggests spacetime itself is quantized at the Planck scale. At extreme speeds, you might encounter this granularity directly. Motion might become impossible beyond certain velocities as you hit the universe's fundamental pixels. Like a video game character trying to move faster than the screen refresh rate, you'd glitch and freeze. The trans-Planckian problem questions, what happens to physics at energies exceeding the Planck scale? Blue-shifted radiation at near light speed would eventually reach these energies. We have no theory for such conditions. Physics itself might break down, making the journey not just impossible but undefined. Vacuum decay could theoretically be triggered by high-energy events. If approaching light speed risks triggering such a catastrophe, the anthropic principle suggests we exist only because the speed limit prevents such disasters. The universe's stability might depend on keeping everything below light speed. The information content of the observable universe is finite, about 10 to the 120 bits. At near light speed, with extreme blue shifting and time dilation, you might try to process information faster than the universe allows. Like exceeding the Bekenstein bound, this could make your existence as an information processing system impossible. The Large Hadron Collider accelerates protons through 27 kilometers of superconducting magnets, consuming enough electricity to power a small city just to reach 99.99999% of light speed. Each proton gains the kinetic energy of a flying mosquito, impressive for a subatomic particle, but revealing how much energy even tiny masses require at extreme speeds. Scaling this up to human-sized objects would require more energy than our civilization has produced in its entire history. Biosignatures from extremophiles on Earth show life adapting to incredible conditions, bacteria thriving in nuclear reactors, organisms surviving in space, microbes living miles underground. But none have adapted to relativistic speeds because such conditions don't exist naturally anywhere in the universe except in particle jets from black holes and supernovae. Life as we know it evolved in a slow, subluminal universe. The Unruh-Davies effect predicts that accelerating observers see particles that inertial observers don't. At the accelerations needed to reach light speed within a human lifetime, millions of Gs, you'd be bathed in radiation hot enough to instantly vaporize any known material. The harder you try to reach light speed quickly, the more the universe punishes you with heat that exists only from your perspective. String theory's extra dimensions might offer shortcuts through higher dimensional space, avoiding the light speed limit in our familiar 3 dimensions. But these dimensions are supposedly curled up at sizes trillions of times smaller than atoms. Accessing them would require energies approaching the Planck scale, the same energies that might destroy space-time itself. Every exotic solution leads back to impossibility. The Kardashev scale classifies civilizations by their energy consumption. A Type 2 civilization harnesses the entire output of its star. Even such an advanced civilization couldn't accelerate significant masses to near light speed. The energy requirements exceed what's available. If beings capable of building Dyson spheres can't achieve light speed travel, what hope do we have? Quantum chromodynamics, the theory of the strong force, shows that quarks can never be isolated. Pulling them apart just creates new quarks from the vacuum. Similarly, trying to exceed light speed might trigger compensating effects that prevent it. The universe might create resistance from nothing, spawning particles or fields that stop acceleration just as it prevents free quarks. The black hole thermodynamics discovered by Bekenstein and Hawking shows that information, entropy, and surface area are fundamentally connected. As you approach light speed, your interaction with the universe's information content might hit fundamental limits. You could literally run out of computational space to exist as a complex system. Warp drives require negative energy density, something that might exist only in microscopic quantities between Casimir plates. Expanding such regions to macroscopic scales might be like trying to inflate a soap bubble to planetary size. Physical properties that work at small scales fail catastrophically when scaled up. The universe permits exotic physics only in doses too small to exploit. The galaxy rotation problem that led to dark matter's discovery shows we don't fully understand gravity at large scales. Perhaps there are similar mysteries at high speeds that make light-speed travel impossible in ways we haven't discovered. Our physics might be missing crucial pieces that only become apparent at relativistic velocities. Cosmic voids, regions of space with almost no matter, span hundreds of millions of light-years. Even at light speed, crossing them would take eons. The universe's structure itself seems designed to isolate regions, keeping civilizations apart. These voids are expanding due to dark energy, making the universe increasingly fragmented and disconnected. The Fermi bubbles, enormous structures of hot gas, extending from our galaxy's center, show that even natural processes don't achieve light speed on large scales. These bubbles, powered by our galaxy's central black hole, expand at merely 3 million miles per hour, fast by human standards but crawling compared to light. If nature with its unlimited power can't do better, how can we? Pulsar timing arrays use millisecond pulsars as cosmic clocks to detect gravitational waves. These natural timekeepers are so precise they rival atomic clocks. At near light speed, gravitational wave interactions would distort space-time around you unpredictably, making navigation impossible. You'd be sailing through a storm of rippling space with no way to chart a course. The cosmic web's filamentary structure means matter isn't evenly distributed but concentrated in threads and nodes. At near light speed, hitting these denser regions would be catastrophic. The universe's large-scale structure itself becomes a barrier, with no clear paths between galaxies that avoid all hazards. Gamma-ray bursts, the universe's most energetic events, accelerate particles to 99.999% of light speed. These natural particle accelerators, powered by collapsing stars or merging neutron stars, show what's required to approach light speed. Stellar masses converted to pure energy in seconds. The violence required makes human light speed travel seem quaint. The cooling of the universe means available energy decreases over cosmic time. In the far future, even if civilizations survive, they'll have less energy available for space travel. The window for achieving light speed, if it ever existed, is closing. We might be living in the only epoch when interstellar travel is even theoretically possible. Dark flow, the mysterious motion of galaxy clusters toward a specific region of sky, suggests large-scale structures beyond our observable universe. Even at light speed, we could never reach these structures or understand what causes this flow. The universe keeps its secrets behind horizons we can never cross, no matter how fast we travel. The lithium problem in cosmology, why there's less lithium than Big Bang models predict, shows our understanding of the early universe is incomplete. Similar mysteries might exist about high-speed travel that we haven't encountered, because we've never achieved such speeds. The universe might have surprises waiting that make light speed even more impossible than we think. The Torella experiment, recreating planetary magnetospheres in miniature, shows how charged particles interact with magnetic fields. Scale this up to near light speed, and the interstellar magnetic field becomes an impenetrable barrier. Your spacecraft would need to generate opposing fields so strong they'd require more power than exists in your entire vessel. Every solution spawns new impossibilities, like a cosmic game of whack-a-mole where physics always wins. Time crystals break temporal symmetry while respecting thermodynamics, showing that even exotic states of matter obey fundamental limits. Similarly, any exotic propulsion method would need to respect the universe's speed limit. We can bend the rules in surprising ways, creating matter that repeats in time rather than space, but we can't break them. Light speed remains inviolate even in the strangest corners of physics. The cosmic neutrino background, relic neutrinos from 1 second after the Big Bang, fills space with particles moving at nearly light speed. These ancient messengers have traveled for 13.8 billion years, carrying information about the universe's birth, yet even they can't exceed light speed, despite having the ultimate head start. If particles born in the Big Bang's fury can't break the limit, how can we? Quantum scarring shows that some quantum systems retain memory of classical orbits, creating patterns in chaos. At near light speed, similar scarring might occur in space-time itself, your passage leaving permanent marks on the fabric of reality. These scars could accumulate, creating resistance that prevents anyone from following your path. The universe might remember and resist repeated attempts to approach its speed limit. The holographic principle's connection to black hole entropy suggests information is fundamentally limited by area, not volume. As length contracts at near light speed, the information content of space ahead of you would compress to infinite density. You'd be trying to process infinite information in finite time, a computational impossibility that might manifest as physical barriers to further acceleration. Axions, hypothetical dark matter particles, would interact so weakly that they'd pass through light years of lead without noticing. If we could somehow become axion-like, would we slip through the universe unimpeded? But even axions respect the speed of light. The universe offers no exceptions, no loopholes, no special cases. Every particle, every force, every phenomenon bows to the same limit. The false vacuum collapse scenario gains new relevance at extreme speeds. Blue shifted vacuum fluctuations might reach energies where our vacuum becomes unstable. Your attempt to reach light speed could literally trigger the end of the universe, expanding outward at light speed in a sphere of destruction. Perhaps the speed limit protects not just causality but existence itself. Magnetic monopoles, if they exist, would revolutionize physics and potentially enable new propulsion methods. Despite decades of searching, we've found none. Their absence might be another way the universe prevents shortcuts to light speed. Every theoretical particle that might help us travel faster remains stubbornly theoretical, as if nature conspires to keep us slow. The measurement of gravitational waves confirmed they travel at exactly light speed, not even slightly faster or slower. This locks down another potential loophole. If gravity itself respects the speed limit, no force in nature exceeds it. We're trapped by the universe's fundamental architecture, prisoners of space-time geometry. But here's the profound truth hidden in all these impossibilities. The universe's speed limit is what makes it comprehensible. Without it, cause and effect would break down, the past could change the future, and reality would descend into paradox. The speed of light isn't a barrier. It's the foundation that allows rational physics, stable atoms, and ultimately, our existence. Consider what we've achieved despite these limits. We've decoded the cosmic microwave background, reading the universe's baby pictures. We've detected gravitational waves, feeling space-time ripple from colliding black holes billions of light years away. We've mapped millions of galaxies, understanding the cosmos's large-scale structure. We accomplish all this while essentially standing still on a tiny rock, using nothing but our minds and instruments. The Parker Solar Probe touches the Sun. Voyager explores interstellar space. New horizons reveal Pluto's heart-shaped plains. We've soft-landed on comets, driven rovers on Mars, and maintained a continuous human presence in space for decades. These achievements seemed impossible to previous generations, yet we did them without approaching even 1% of light speed. Perhaps the real message isn't that we can't reach light speed, but that we don't need to. The universe comes to us through light, gravity, and particles that cross vast distances to tell their stories. Every photon carries information across space and time. Every cosmic ray whispers secrets of distant supernovae. We explore the universe by bringing its messengers to us, not by racing toward them. The night sky isn't a barrier but an invitation. Those points of light aren't destinations we'll never reach but messages we're already receiving. When you look at a star, you're seeing its past, true, but you're also touching it through the electromagnetic force, connected across light years by fundamental physics. We're not isolated, we're embedded in a web of light that connects every star to every eye that looks upward. Future technologies might seem like magic to us now. Perhaps we'll find ways to explore the universe that don't require speed, quantum sensors that can taste the composition of distant worlds, gravitational wave telescopes that hear the universe's hidden songs, or something we can't yet imagine. The impossibility of light-speed travel might push us toward possibilities we haven't dreamed of. Remember, we are made of stardust, atoms forged in stellar cores and scattered by supernovae. We don't need to travel to the stars because we are the stars, reassembled into conscious beings capable of understanding our origins. The universe doesn't just contain us, it expresses itself through us. Every question we ask, every mystery we probe, is the cosmos examining itself. The speed of light isn't our enemy but our teacher. It shows us that the universe has rules, that reality has structure, that existence makes sense. It forces us to be clever rather than fast, to think rather than race, to understand rather than merely arrive. Perhaps civilizations that accept this limit achieve something greater than those that rage against it. So yes, we will never travel at light speed. The universe's architecture forbids it through every law of physics we've discovered. But this limitation doesn't diminish us, it defines us. We are the species that figured out why we can't go faster, that understood our limits so precisely we can push against them optimally. We turn impossibility into knowledge, barriers into understanding. The next time you see stars, remember, their light traveled for years, centuries, millennia to reach your eyes. You're already engaged in a cosmic conversation across impossible distances. You don't need to travel at light speed. You're already touching eternity every time you look up. The universe has come to you carried by messengers that respect the cosmic speed limit but transcend every earthly barrier. Thank you for joining me on this journey through the beautiful impossibilities of light speed travel. If this exploration has changed how you see our place in the cosmos, please share this video with someone who dreams of the stars. Subscribe for more deep dives into the universe's mysteries, and remember, we might be forever slower than light, but our curiosity and wonder know no limits. What other cosmic impossibilities should we explore next? Leave your suggestions in the comments below. Until next time, keep looking up, keep asking why, and never forget that understanding our limits is the first step to transcending them. We are stardust contemplating starlight, forever bound by physics but freed by imagination. If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you want to keep exploring the mysteries of the universe, I am sure you will love this other video at the left side of the screen. What if the speed of light changed? Discover how even a tiny change in light speed would unravel atoms, destroy stars, rewrite the laws of physics, and reshape the entire cosmos. See you there.